Ba-da-boom! It's the morning time. What are you gonna do? Probably go back to bed. Okay, we're here talking about AP Physics C, electricity and magnetism, and this is going to be the start of a number of videos that dive into what is known as Gauss's law. Okay, now Gauss's law has a number of different uses, but before we get into like the mathematics of Gauss's law, we need to talk about an idea of flux. And when we talk about flux, what we're really talking about is something coming into a region or out of a region. I like to think of this as a bathtub. If you turn on, your faucets or your spigots for the bathtub, you can start filling the tub up. This would be like an influx of water. So flux is coming in. We can call it like a positive flux. So you're filling up the bathtub, flux in, flux in, flux in. You're gaining this water. The water is coming in. That is the flux there. And then if you wanted to, you could pop the stopper on your drain and then all the water could go out. And when the water leaves, now you have a flux leaving the system because the water is leaving the system, it's leaving the bathtub, and that's some negative flux. And if you have a perfect bathtub setup, then your water as it comes in will directly flow out, and that's it. So you have a net of zero flux. You're never gaining or losing anything. It's just always staying constant. So that idea of flux is very important. We're going to use this idea of flux for Gauss's law with electric fields, but you can also use this idea of flux for Ampere's law when you talk about magnetic fields or B fields. So this idea of flux, it's something coming either into a system or out of a system, or the way we like to think of it is passing through a surface. So if you have something such as a field passing through a surface, we can call this a flux, and that'll become really important to us. Now, when we talk about fluxes passing through a surface, we need to define a surface like in and of itself. So let's just draw a surface here. This is going to be like a flat plane. Okay, so here's a plane, going in the x-y directions. And if I asked you, like, what direction is the plane itself? That's kind of like, what? Like, what are you... You're talking about, like, x, y? Like, is it, like, left, right, up, down? Like, what are you asking? I don't know, like, what is the direction of the plane? Like, what is its orientation in space? Because, as we see here, there's, like, 4 sides of it, and there's all sorts of stuff in the middle. Like, what is its actual orientation? The way we mathematically define the orientation of a plane is with a vector normal to the surface of the plane. So if this is the plane here, we actually define it as saying, look, this here, this normal vector, which we'll say is n with a hat on it, this is n hat, maybe I'll draw my n a little bit better, n hat, that's the normal direction vector. Okay, and it represents that, hey, look, this plane is facing up. And think of it this way, if you're sitting at a table right now, like the top of the table is pointing to the ceiling. If you took the top of the table and had it pointing sideways, like to a wall, well, your table would be sideways. And that's what we'd see here with the normal vector. Your table's pointing 90 degrees to the side. So this is the idea of a normal vector and how we designate the direction of a plane, which is a very important thing for us. The reason why it's such an important thing is when we think of flux, we think of flux as moving through the plane. So we have these flux lines coming up, and they're passing through the plane like this. Okay? Now, they can pass through the plane. So this flux right here, we'll call this our electric field, because that's what's going to act as our flux in this case. Notice that this electric field, the flux here, is in the same direction as the normal vector. They're parallel. Okay? Even if the flux was coming down, like let's say you had some flux coming down here, like that, this flux would still be parallel to it. Okay? It's not going to intersect. It's not running like that. Now, the reason why it's so nice that these flux lines are able to pass through the surface is simply because, imagine if I tilted this sideways. So here's our plane now, and here is the normal vector. If the flux was moving like this, or up, whatever, it wouldn't pass through that surface. And we actually wouldn't have a flux then. We would just have an electric field. We wouldn't actually have a flux. So it turns out that the way we think about flux is the amount of this field, this electric field, that passes through the surface in the direction of the surface. Okay, so it's the amount of flux passing through the surface parallel to the direction normal of that surface there, which means that flux, which we can draw as a capital phi, of an E field, we subscript it with an E because it could be a B field, but this is an electric flux, is equal to the electric field dotted with the area. Because if I have a larger shape or a larger area, I could get more of this E field through it. And remember, this dot product represents the cosine term. So this is going to be E, whoops, this is really just EA, these are magnitudes here, times the cosine of theta. Okay, so we're really thinking about the electric field passing through the surface in the same direction as the normal vector. Okay, so that's what's going on here. The electric field passing through the surface in the same direction as that vector. So we're going to get a cosine product out of that. And that makes sense, because if we take a look at this, imagine we had a flux kind of coming up at an angle like this. If it came through here and this was some angle being made here, then this is the adjacent side of that angle. So this would be the amount I would want to find. Okay, that's the amount right there that I would want. So it is that cosine term that we're looking for. Okay, so that's the idea of a flux here. Now, when we take a look at some of these shapes, while this is the idea of flux, it is helpful to think about a tiny little segment of area. So if we have a tiny segment of area here, it's going to get some electric field moving through it. But because that area is so infinitesimally small, we'll call it dA, it's a small segment of area, it's only going to get a small little segment of the E field. So it's only going to get a little dE going through it. And what this will mean is, if we kind of think about this, well, maybe I shouldn't say that's dE. Let's not say that. Let's just say this E field's uniform. This is a uniform E field. That's the problems we're going to get this year. This is still going to get an E field rolling through it. Okay, but it's a small area, so we still get the E field, but a small area here, such that when we take a look at this flux, we're only going to generate a little bit of flux. So this tiny bit of flux from the electric field is going to equal our electric field, and then this is going to be some dA, some small little piece of dA. And remember, this is technically a dot product here, which is going to equal E dA cosine of theta. Okay, so we are using uniform E fields here. It makes the mathematics much more straightforward. Otherwise, you start getting into very difficult problems. If you're seeing this at a collegiate level, maybe you'll see this as, you know, an E field as a function of radius or as a function of x comma y. But at our level right now for AP Physics C, we shouldn't see that. So this is what we kind of see here. Okay, we've got a tiny segment of flux equals E dA cosine of theta. And if we were to add up all this flux, all these little tiny segments of flux here, so if we were to add all of this up, we'd get this back. And if we're adding things up, then what we're really talking about is just an integral, right? If we're saying that, look, our flux here, our electric flux, is the addition of all of this flux here, well, fancy addition we can write as the integral symbol, which means that our integral comes everywhere. And then what we're really saying then, if we look at out here, is that the flux is equal to some integral of E cosine of theta dA. Now, the interesting thing about this integral is that when we're adding up, what are we adding up here? Well, we're adding up areas, okay? We're adding up these tiny little segments all across the surface. And what this means is we have a surface integral here. So we could write this, some places write this as like an S down here for a surface integral. In the end, though, what you're really thinking about is that, look, if this is just some surface you're adding up to get the area, then assuming everything else is constant, then what you're going to have here is that our electric flux is just going to equal E cosine theta times whatever your area is, which is no-brainer. Like, that's what we have up here. Like, we already wrote that. This isn't anything crazy. but it's whatever that area of the surface you're passing through is, okay? Hopefully, what we can do is if we set up a surface in such a way that the E field is always passing through normal to it, then this cosine term will become the cosine of 0, which equals 1, and we can get rid of it. That's a nice goal for us, because then we can just say that this surface integral here is just equal to E times some area. And that'd be really nice, because I know areas of things. That's not too hard to do, okay? But really, this integral of dA is just an area. It is just an area there, okay? So why would this become effective? Well, if this is a surface area, and what we're looking for here, what we will do is we will write Gauss's law like this. We'll actually consider it as a surface integral, and what we'll say is that this flux of the electric field equals a closed path integral, or a surface integral here, because I'm just integrating over a surface, of E dot dA. Okay? This is Gauss's law right here. And this is what we'll need as we move on into some later videos. So this one was just setting up what is this idea of flux, what is this idea of a surface integral, the surface area here, what are we talking about? This right here at the very end, this is the equation that we'll be using as we go further on. And it does actually equal one other thing, but we'll see that in the next video as we start diving into some examples and getting deeper into the world of Gauss's law. But until next time, adios and take it easy.